Single replacement reactions are something we've studied earlier on in the chapter, but at the time we were introducing those kinds of reactions, we at no point ever mentioned the fact that not all single replacement reactions can actually happen. So now's the time to introduce this concept of what's called the activity series of metals. It's located on your solubility table, upper left-hand corner. The reaction we're going to talk about first on your sheet is when nickel metal gets added to a solution of silver nitrate. And silver nitrate, as you can tell on your sheet, is a solution, which means it's soluble, which means that you won't actually be able to see silver or nitrate in the solution. It'll look essentially like a water-based solution. So the visual is you've got a beaker that contains a clear colorless solution that looks like water. In that solution there are silver ions and there are nitrate ions floating around amongst the water molecules. The silver ions and the nitrate ions are both aqueous. They're both surrounded by water and they're invisible. What you want to know is this. If you put a piece of nickel, so picture a substantial little nickel rod that you can actually see and bend and touch. If that piece of nickel metal went into the solution, what we want to know is, would there be a reaction? Would the nickel atoms that right now are neutral lose electrons and become nickel ions, and would the silver atoms that are in solution actually gain electrons and go back to be silver atoms? We want to know, will that happen? So to answer that question, we have to go to our solubility table, and you've got to find both of those metals on the table. So here's the nickel, and the silver ion is located on the right. Now to read the table, what you need to know is that the nickel, or the metal that's by itself, the single element, must be higher in the table on the left-hand side. So look at the nickel compared to the silver. It must be higher than the silver ion on the right-hand side that's in the compound that it's trying to replace. And since the nickel metal on the left is higher than the ion, this reaction will be spontaneous. And you will see signs of the chemical reaction. Maybe you'll see a change in color. Maybe you'll see a certain amount of heat being produced from this reaction, because it can happen without any added energy. So to complete the reaction, once I know that it can happen, it becomes very much like every other reaction we've done. Nickel as a solid is going to react with silver nitrate, which is an ion, and an aqueous ionic solution. And the product you're going to get is going to be the nickel coming into the compound. And nickel, as you can see on the table, from what you know from chapter 6, nickel becomes a nickel ion. And nickel ions always have a 2+ charge. So consequently, when it comes together with a nitrate, you need to balance that and make it NiNO3 taken twice. And you should recall that all nitrates are soluble, so that's going to stay aqueous. And the other product will, of course, be silver coming out of solution and being in its pure elemental state. It will actually look like pure silver. And you'll be able to see it shiny, typical color, and all that. There's your skeleton equation. It is not balanced. We can do that easily enough. We have 2 nitrates on the right, we need 2 on the left. And therefore we need to have a 2 in front of the silver to balance the silver atoms. So 1, 2, 1, 2 based on the order that I have written it. I always get the question, could the silver come first and nickel nitrate come second? Of course. The order does not matter on the product side as long as both reactants are there and they're balanced correctly. So looking at your table, the nickel metal on the left-hand side of the table was higher than the silver ion that it was trying to replace. The second example we'll do is similar, and the question in your booklet is about aluminum in an acid solution. So if you put a piece of aluminum foil as a solid into an HCl solution, say hydrochloric acid solution, AQ, a concentrated acid solution, will it happen? The very first thing you need to do is go to your table for activity series of metals, and you need to look up and find your aluminum. Aluminum is quite high on the table, which makes it quite reactive. The hydrogen on the table is in its ionic form here on the right. And it will turn into, if the reaction happens, hydrogen gas, and the aluminum will turn into the aluminum ion. To decide the question if the reaction will actually happen, you've got to say, is the metal higher than the ion? And it is. Therefore, this reaction is indeed spontaneous, which means it will proceed. To show that, we can actually write the products. So aluminum as a solid will react with hydrochloric acid. Doesn't really matter what the acid is as long as it's strong enough. HCl. And the aluminum will come into the compound and the hydrogen will come out. When the hydrogen comes out, it becomes H2. 2 because of the diatomic stability, and it will be a gas. You'll actually see bubbles. And the other product will be aluminum, when it loses its ions, becomes a 3+. And the chloride's a 1-, so it's going to be AlCl3. On the bottom of your table, you'll find your solubility rules. And most chlorides are soluble, with the exception of a few, and aluminum is not one of them, so it's going to be an aqueous compound, invisible in the water environment. To balance the equation, you need to look at the fact that on the right-hand side, we've got 2 hydrogens and we have 3 chlorines. And those are equals and opposites together on the left. They're together as a compound, so you need to make a common multiple of each. Let's say 6. Therefore, if you put a 3 in front of the hydrogen and a 2 in front of the aluminum chloride, that gives you 6 for each, which is easily balanced, and the aluminum will require a 2. So 2, 6, 3, 2 will balance this equation. And again, it was spontaneous because the lone element that is on the left-hand side of your reaction must be higher than the ion that it's trying to replace. The element's higher than the ion. And if it isn't, it will not react. It will not happen. A couple more examples to show you this. On your sheet, you have 2 questions that say, will these proceed? The first one is magnesium metal. If that was put into an iron 2 nitrate solution, and that's aqueous. The question is, will it proceed? So you go to your table and you find your lone element, and it's up here, magnesium metal. And the ion it's trying to replace is the iron ion here. Since the metal on the left is higher than the ion on the right, the reaction will happen, and it is spontaneous, so you can finish it. The magnesium will come in, give the boot to the iron, so you're going to get magnesium in the compound. Magnesium, as you can see, but you'd already know, is a 2+ ion. So with the nitrate, it's going to stay as 2+, MgNO3 taken twice. All nitrates are soluble, so it's going to continue to be in a water environment, and the iron is going to come out as solid iron, which is what happens when the equation is written in reverse. That reaction is spontaneous. The question was, will it proceed? And the answer is yes. The reaction will definitely proceed. The second one on your page is asking if you put gold as a solid in an HCl solution, will there be a reaction? Will it proceed? Will it happen? So to compare these, we'll find them on our table. Gold's at the bottom and hydrogen is below it. This is the first example on these out of these questions where the metal is lower in the table than the ion. And that's exactly what will be the case when the reaction will not happen. You can put as much gold as you want into a vat of acid. It will not react because gold does not want to oxidize. There will be no reaction. On the product side, you don't do the reaction. You simply write no reaction, or in some books, they abbreviate it NR. It will not happen. The reaction will not proceed. Not going to happen. And the remaining question on this page, your notebook page, about these reactions is a bit of a unique case. Let's do it together. It is potassium metal. Potassium metal placed into water. Will the reaction happen? I showed you this reaction on a YouTube video back in the very beginning of the course, and I want to remind you that it happens, and it happens quite vigorously. What you've now learned about equation skills should help you in that in single and double replacements, it's quite often to our advantage to write water as HOH. And that being, if that's the case, I now want you to look at the activity series of metals and see that the potassium is very high, much higher, of course, compared to the hydrogen ion that is trying to replace. And since it is higher, the reaction is spontaneous. When the reaction proceeds, what you're going to get is the hydrogen getting removed, coming out as H2 as a gas, stable as a diatomic, and the potassium going with the hydroxide, KOH, and that, of course, all group 1s are soluble, so it's aqueous. To balance this, the only thing that is not balanced right now, the only thing that is not balanced is the hydrogen. I have 2 on the left. Sorry, I have 2 on the right, and I need 2 on the left, so I'm going to put a 2 in front of the water. That's going to give me 2 H's, and that's also going to give me 2 OH's. So now I have to backtrack and put a 2 in front of the KOH to give me 2 OH's on the right. Then I'm going to go backtrack and put a 2 in front of the K to give me the overall equation of 2, 2, 1, 2 to balance. And as you can see here written on the side, potassium will react with cold water, and quite vigorously, in fact. So be careful. Now the last thing to talk about is what happens when you're trying to figure out the procedure for replacing nonmetals with nonmetals. Every example before this has been metals with metals, and now we're going to do metals with nonmetals. And it's very simple if you know how to read your periodic table. So if you look at your periodic table in the group 17, we've got fluorine on the top, chlorine, bromine, and iodine in that order. The higher up that it is, the more likely that it's going to be reactive. It's a smaller atom, and it'll react more easily. Therefore, when you're looking at a question, you've got to always make a judgment call. Will it happen? Will it not? In example number 4, chlorine as a gas, is that gas going to be higher in the table than what it's trying to replace, the iodine? And yes, it is. Therefore, it will proceed. It will be spontaneous. You're going to get the iodine coming out as a diatomic and as a solid. And you're going to get the sodium pairing up now with the chlorine, 1 plus 1 minus, in a water environment, so it's going to remain aqueous. The equation isn't balanced, but it can be by putting a 2 in front of the NaCl and a 2 in front of the the sodium iodide, and that'll balance your overall equation. So for when you're getting a question that has a halogen trying to replace a halogen, the decision comes from the position in the table. Example 5, you want to know, can the bromine replace the fluorine? Well, bromine is lower in the table than fluorine, so that reaction will not happen. It's non-spontaneous. Unless you add energy, there will be no reaction. So the activity series comes from actually the periodic table for nonmetals and nonmetals. But for metals and metals, you want to use the activity series of metals, and that table is only good for single replacement reactions only. Thank you.